All right, go ahead and send it in if you haven't yet. All right, anybody else? Okay, good. So 95% of you are saying B, resting expiration. Okay, so when you're when you're letting your breath out, when you're not exercising, resting expiration, that's correct. Okay, and the reason for that is because number one, your lungs are elastic. Okay, so when we stretch them out and take in a breath, elastically they want to bounce back, and when that happens, it pushes the air out. And our diaphragm is the other reason for that. So our diaphragm is a domed muscle, kind of up like this, right? And when we contract it, it flattens out, and when we relax it, it goes back into its dome shape and kind of pushes back up. Okay, so in the combo of our lungs kind of retracting back because they're elastic, and our diaphragm pushing back up, and our chest cavity actually falling back down, all of those things together is what pushes the air out. So it doesn't actually require any contraction, just relaxation of muscle to do that. If we want to do it faster and more forcefully, like when we're exercising, then we can use some muscle to make that happen faster. But at rest, it doesn't require any of that. Okay, so how do we breathe? What are the mechanics of breathing? So first of all, the idea is air is going to flow from a high pressure area to a lower pressure area. Just like we talked about kind of with diffusion, right? High concentration, low concentration. Blood pressure is the same way, right? Higher blood pressure is going to push down to the area where there's lower blood pressure. Same thing with air, right? So high pressure to low pressure. Okay, so the whole point of our breathing muscles and everything we do is all about changing pressures so we can create a low pressure situation in one place or a high pressure situation in another place so air moves. Okay, so the way we breathe is by changing first of all, the volume in our thoracic cavity. So that's not necessarily our lungs yet. That would be the space like around our lungs. Okay, and then by changing that volume in our thoracic cavity, that changes the volume inside of our pleural cavity, which is that space we talked about last time. Remember, we have those two, the visceral side of the parietal, or the visceral side of the pleura, and then there's that space in the middle with the fluid, and then there's the parietal side. So that pleural cavity changes, and then that changes the pressure inside the pleural cavity. So the volume affects the pressure, right? So we're changing the size of it, and then by changing the size of it, that changes the pressure. And then that change in pressure inside the pleural cavity then changes the volume inside of our lungs. And then if we change the volume inside of our lungs, now we're changing the pressure inside of our lungs too. And we're going to make that pressure inside of our lungs be different from the pressure outside in the air. If it's inspiration, we want to make the pressure inside lower, so the air goes in. If it's expiration, we want to make the pressure inside be higher than the pressure outside, so the air goes out. Okay. All right. So how do we do that? We do that with our breathing muscles. Okay. And so here's a bunch of them here. Okay. What I want you to do for a sec with the people on your team is just go through this list. So these are all actually just the names of muscles. So we're assuming that's them contracting. Diaphragm has two lines because it's one with diaphragm contracting, one with it relaxing. Okay. And so take a guess on what you think here. Just write an L or an S next to each one. L meaning that by contracting one of these or by doing whatever this says, that the cavity, thoracic cavity gets larger, or S if it gets smaller. Okay, and you can use this image on this side to help you with this a bit. Okay, go ahead, do that for a couple minutes, and we'll come back together in a sec.
Yeah, I did something. Oh. Next. Yeah. It's like the big one. It's what it's kind of like. Wait, which one were you looking at? Okay, it's like. Sorry. Diaphragm relax. Yeah.
All right, let's go ahead and come back together here. Okay, so what'd you guys say for the diaphragm contracting? Does that make it larger or smaller? Not sure. So we were just talking about when it's a domed muscle, okay? Is this the contracted state or the relaxed state? This is relaxed. Yeah, so when we contract it, it flattens out actually, right? Which that makes this space bigger, right? Because this will be smaller, that makes it bigger. So the diaphragm contracting makes it larger. Diaphragm relaxing is going to push back up and shrink this space, right? So that would make it smaller. Okay. Our external intercostals, we can see them here, right? They're connected to these little blue arrows. So what would that be doing? Making it larger or smaller? Larger, yeah, for sure. How many people like ribs when you go to like a barbecue place and eat ribs? Yeah, yeah, you're eating intercostal muscles. That's what you're eating. Yeah, that's what it is. Right? It's the muscles between the ribs. That's the intercostals. Okay, so we got that. They're still good. Doesn't matter. Just want to make sure you know what you're getting into. Okay, pectoralis minor. All right, what'd you guys say there? Larger or smaller? Larger. Another one that lifts up the rib cage, right? So we're seeing that there. Okay, what do we have next? Sternocleidomastoid. What'd you say? Larger still, another one that's lifting up the rib cage, right? And then we got the scalenes all in there too. I already circled them, right? And then we've got the internal intercostals. See them over here? Pulling down now, right? Those ones, the angle is such that they pull downwards, so those would make them smaller. Let's go back here. So these are all larger, 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 smaller. And then the abdominals, right? Pulling downwards here. So smaller as well, right? Okay. So that's just kind of the way to think about these muscles and what they're doing is they're changing the size of the thoracic cavity, which then is going to change the pressure. Okay. So the passive one we talked about would be resting expiration. Okay. And then the other three options, which would be both expiration and inspiration. Both resting and we'll just put X for exercise. And then this one, just the exercise one. So you could call it active expiration or active inspiration, or we could just say it expiration or inspiration during exercise. That's why I have the EX there. Okay, or sometimes it's called forced expiration, forced inspiration. Okay, questions about any of that? Or what I wrote? Yeah, listen. Very bottom says resting / exercise inspiration. So both types of inspiration require contraction. Any other questions? Okay. So then let's go on to the next, which is the diaphragm. Okay. The diaphragm is a type of skeletal muscle. Okay. It's voluntarily controlled. right? So it's not smooth muscle, obviously not cardiac muscle. It's voluntary muscle. We can actively control it, okay? And it's very special because it's the most oxidative of any of our skeletal muscles, meaning that it has the most mitochondria of any skeletal muscle. What property would that give it if it had the most mitochondria? What would you say about it then? High aerobic capacity, for sure. Most resistant to fatigue, right? That's good, right? We don't want our diaphragm to wear out. That we'd be in trouble if it fatigued and didn't work anymore. Okay, so it's not very likely that it's going to fatigue. And this is a nice little GIF that kind of shows us what it does, right? It totally changes the size of the thoracic cavity because it's the floor of the thoracic cavity, right? So we're just moving the floor down, moving it back up, moving it down, moving it back up, and it totally changes the size there. Yeah. Taylor?
When you breathe in super deep, does it like move your organs around at all?
It does, yeah, for sure. Yeah. Yeah, it definitely puts a little bit of pressure on your abdominal organs and kind of just shifts them down just a little bit. Especially like if you were laying down and then your organs would kind of like shift upwards. And then you take a deep breath in, it would kind of push them back down a little bit. Sure, when you're standing up, they're already kind of rest downwards because of gravity. But yeah, if you were upside down and took a deep breath, then it would definitely do that. Yeah, it would definitely. You have to. That's why it's harder to breathe when you're upside down. It's because you're lifting up your abdominal organs with your diaphragm. Yeah, it's a good question. Other questions on this? Okay, so then all of this idea of changing volumes and pressures is all related to this gas law called Boyle's law. Okay, so Boyle's law is defined as when the amount of gas is constant, pressure and volume have an inverse relationship, right? That's the key part. Pressure and volume have an inverse relationship. So the little image on the left there shows two different beakers that have air in them. Okay, and then there's like a little plunger on top that can change the size of the chamber that holds the air. Okay, and so you can see pretty much the idea of pressure is how often when it's air pressure, gas pressure like this, it's the idea is how often do the air molecules strike the sides of the container, right? And if they do it more often, then the pressure is higher. If they do it less often, then the pressure is lower. And so the one on the left here is showing double the volume, but with the same amount of air. We go to the right, it's half the volume with the same amount of air. So this one is going to have double the pressure, right? Times two, sorry, the other way around. This one's going to have times two the amount of pressure. This one is going to have half of the amount of pressure as the other one. Okay, so if we go from the left to the right, we're decreasing the volume. We're cutting the volume in half, so then the pressure doubles, right? Because the air inside is going to strike the walls twice as often because there's half the amount of space for it to move around. Yeah, Morgan. So like in our lungs, when we take a breath, right, and we take air in and then we let air out. Yeah, but we're still going to apply Boyle's law to our lungs, but yeah. So this is kind of a model of what our lungs are like. So we've got the diaphragm on the bottom, got these little balloons kind of representing the lungs, and then the space around the balloons would be similar to that pleural cavity and that serous membrane around our lungs. And I actually brought in a little toy for you guys to play with too. That's a similar idea here. Okay, so this is a lung model as well. And so the plunger represents the diaphragm. Okay, the balloon represents the lungs, and then the space around the balloon represents that pleural cavity. Okay, and so what we can do is there's air in both, right? There's air in the balloon and there's air around the balloon in that pleural cavity. So if I move the plunger downward, what am I doing to the volume of the pleural cavity? Going up, right? Same amount of air in there. around the pleural cavity. So that pressure is going to decrease, right? And pretty much it creates a vacuum around the balloon, right? So when I pull this down, the balloon fills up, right? Because there's a vacuum around the balloon and the balloon walls are pulled open by that vacuum, right? Which is exactly how it works when our diaphragm pulls down and that, yeah, and then that pleural cavity opens up. It pulls the lungs open by creating a vacuum, creating like a negative pressure, making sure that pressure is lower in that pleural cavity versus the lungs. And then just the opposite, sorry, when we, when we exhale, it does the same. We decrease the volume and it increases the pressure. And so it pushes the air out, okay? You guys can pass this around and play with it a little bit as throughout the rest of class. But yeah, so that's Boyle's law. And so the way that this is applied to the lungs is, first of all, we have our three spaces really, right? We have the atmosphere out here. Okay, so oops, atmospheric air. Okay, that would be one space that we're interested in. We have our pleural cavity space in here. That's our other space we're interested in. And then we have the lungs. So the space inside the lungs, right? Three different spaces. We won't get into too much detail about the pleural cavity in this class, but the idea is when we're not breathing, the pressure in the lungs is going to equal the pressure in the atmosphere. All right, so about 760 millimeters of mercury in each because air is not actually moving, right? So no movement of air. Okay, so that's just kind of our starting point. All right, and then we're going to move over to inspiration. Yeah, so then with inspiration, we can plug in our muscles, right? So it's going to be primarily the diaphragm contracting, right? It's going to be those external intercostals. And then we can talk about neck muscles and stuff if we wanted to for really forced inspiration. But those muscles, as you guys already said, are going to increase the volume, right? So they're going to increase the volume in the thoracic cavity as well as the lungs. And then we'll come back to Boyle's law here. If we increase the volume there, what has to happen to the pressure? Decreases, right? This inverse relationship between pressure and volume. So the pressure decreases, right? So now we have higher pressure. Sorry, we have higher pressure outside than we do inside the lungs. So air is going to flow in, right? So we've created this kind of negative pressure inside of our lungs by just opening them up, right? By making the volume bigger, pressure goes down. And now we have a pressure difference. So if our mouth's open, then air is going to flow in. Volume goes up, pressure goes down, air flows in. Okay. Questions on that? Okay. Why don't you guys do the next slide? Go ahead. You can fill in the expiration muscles, fill in what's happening volume, pressure-wise, and then we'll come back together in a sec. Okay. Go ahead. Check with the people on your team.
I just got my appointment for my foot, so I'm.
That's a
trying to
good
think.
thing. Yeah. 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 Yeah.
It's actually hard.
It's kind of hard. I know. I need to like put some grease in there or something. But yeah, it's pretty hard to move. Yeah, to kind of force it to reset it. Yeah. What's that? Oh, external intercostals. Yeah.
Are we reading our words or are we reading these our words? Like our. Yeah.
All right, what muscles did you guys fill in there for the expiratory muscles? Say anything about the diaphragm? Diaphragm relaxing, right, is key. Okay. Which of the intercostals work here? Internal. Okay, we could say the abdominal muscles too. Yeah, so those are the main ones. Okay, so with expiration, diaphragm goes back up, right? Chest cavity kind of falls back down. We can pull it down faster with the abdominal muscles. So what kind of a change in volume do we get there in the lungs? Up or down? Down, right? So we decrease volume. What does that do to pressure? Makes it go up, and so air flows out. Right? So if we get more pressure in the lungs than we have in the atmosphere, then air is going to push out. Okay, so just remember that Boyle's law, that inverse relationship between volume and pressure of a gas. Okay, questions about any of that? Okay, all right. So we talked about ventilation last time. And so talk about a few factors here that are related to ventilation, and then we'll wrap up. So one of the factors is called lung compliance. Okay, so lung compliance is the ability to stretch and expand the lungs. Okay, so when we take a deep breath in, then the volume of our lungs opens, right? Our ability to do that, to open up our lungs, is based on how compliant they are, right? How much ability they have to stretch. Okay, so some of the things that affect compliance, one of those would be asthma. Okay, the cause of an asthma attack is typically going to be that our airways are too sensitive or overly sensitive to some type of allergen that gets in to our lungs. Okay, and then that makes our bronchioles get inflamed like this. And then one of the consequences of being inflamed is then the smooth muscle contracts around the airways, and so it constricts. And when you have that smooth muscle squeezing down the airways and you're trying to open them up, it makes it hard to open them, right? Because the smooth muscle is squeezing down on it. How many people in here have asthma or have a inhaler in your backpack right now? Yeah, that's a good question. Yeah. It's different because there's not necessarily a specific allergen that causes it, but it's just the rapid passage of air over your bronchioles that inflames them. So it's still something that inflames them, but it's not like a cat dander or something like that, or pollen, but it's just the air moving rapidly back and forth over your air passageways. Yeah. Hmm. Yeah. And so then albuterol is the kind of the um, most common rapidly acting drug for asthma. Now, albuterol is an agonist of your sympathetic nervous system, right? It activates your sympathetic nervous system. Some of you that have asthma and have taken albuterol know that sometimes your hands get a little shaky, right? How many people know what I'm talking about? When you take albuterol, you get like a little bit shaky because it activates your sympathetic nervous system, right? And remember, the activation of the sympathetic nervous system in your airways is to open up the airways, right? So that's what it's trying to do, is to try to go against that contraction of your smooth muscle and let them relax. But it also can kind of spill over into your bloodstream a bit, and then you kind of just get a little bit hyped up because you've got extra adrenaline going around your bloodstream. Okay, so yeah, it's hard to inhale because we can't stretch out our airways because we got that smooth muscle clamping down on it. Anybody from the Central Valley here? Fresno, Modesto, Merced, any of those areas? Nobody's from Central Valley? Okay, we usually have some Central Valley kids. The Central Valley, the San Joaquin Valley is one of the highest incidences of asthma in the world. And it's because of the air quality. And it's like 1 in 4 kids has asthma in the Central Valley. And that's where my wife's from. And almost all of our nieces and nephews there have asthma. And it's pretty devastating. And most of it is just dirt in the air. Most of it's just dust because of all the agriculture and farming. And there is some contribution from the cows burping. If you've heard of that, the gas the cows release is part of it too. But a lot of it's just the dust in the air. Yeah, so other things that affect compliance would be obesity, pregnancy. That's just kind of what we were talking about with your question, Taylor, which is like you have to lift up everything on your chest to get air in, right? So the more weight you have on your chest cavity, the harder it can be to lift all that stuff up. Chronic bronchitis is just chronic inflammation of your airways like this. Can be caused by smoking, other allergies, other things like that. And then you also get a lot of mucus in there too. So then the airways are smaller because there's so much mucus in there. Lung cancer for sure, collapsed lungs, all leads to decreased compliance of your lungs. Okay. And then the other factor is the elasticity piece, right? So compliance is how much we can stretch it out. Elasticity is how much it bounces back. Okay, and so that's the rebound portion of it. Okay, one of the biggest things that can affect it is emphysema. Emphysema is one of the most common causes of chronic obstructive pulmonary disease, which is COPD. And the deal with emphysema is your normal alveoli look like that, right? So a bunch of individual little sacs, kind of looks like a little bundle of grapes. With emphysema, all of those internal walls of your alveoli break down, and you end up with these very large sacs instead. Okay, and so then normally when we breathe out, we can kind of push all these down individually, right? And that's what we do when we decrease volume. We're just smashing those little alveoli down just a little bit individually. But when we have this big space, we can only push it down so much, and it leaves a lot of extra space in there, right? And so, yeah, so which a little connector to last class, look back at those pulmonary volumes we were talking about. Which of the lung volumes would increase in emphysema? Talk with each other about that for a second. Remember that little graph at the end of last class's notes? Which of those volumes would increase with emphysema?
Could it be?
Aaron, you can put the abbreviation into your clickers. How about that? I'll open it up. You can put the abbreviation of that volume into your clickers. There you go. Kind of takes some effort to pull it, yeah. Yeah. There you go. Yeah, you won't break it. You can pull it hard. Team effort, maybe. Yeah. There you go. Yeah. Yeah. There you go. All right. So put in that abbreviation of the letters that represents the volume and hit send. And tell your teammates why you chose that one. All right, looks like we got most of you. So 44% of you are saying residual volume, RV. And then we've got one saying ERV, which would also be true. I mean, 7 of you saying that. Total lung capacity would not be true because you still got the same amount of space in there. But yeah, so the main one would be residual volume. I won't put it on the bottom. All right, so residual volume was the amount of air that you can't get out of your lungs, right? And as these alveoli go from little individual sacs that we can smash down individually to this big one that we can only smash down this much, right? There's a lot more space in there that we just can't collapse enough to push the air out, so that residual volume goes up. So what that means is every time we bring new air in, to take a breath in, it mixes with that residual volume, which is what happens all the time. But the more of it there is, then the lower the actual oxygen percentage of the areas that we're actually using to extract oxygen from, because it's mixing with that air. So yeah, so it actually takes a lot more work to push air out. And just like the donor we have over here in the lab that you guys saw last semester, the male has that barrel chest, kind of like this. And so have to work a lot harder to exhale than normal and to inhale, because this decreases decreases the ability for the lungs to bounce back, right? So you got to work really hard to kind of squeeze the air out and then take another breath and push hard to squeeze that air out. So it takes more energy to breathe. Also leads to heart failure and damages the pulmonary capillaries. This is primarily caused by smoking, but there's the genetic component as well. Questions on any of that? Okay. Okay, so another one is called surface tension. Okay, so surface tension, we mentioned this a little bit last time. The idea of surface tension is like the thing we talked about last semester with the properties of water, right? Where that water strider was walking on the water, and the water just kind of bending under its feet, right? Because the water molecules are sticking to each other, right? Those are those hydrogen bonds. Those H2O molecules can stick to each other. Our alveoli are so small that water lining the walls of our alveoli, those little molecules, if there's nothing to get between those hydrogen bonds, then the water molecules actually stick to each other like across the way from one side of the alveoli to the other, and it pulls the walls of the alveoli together. So we need a special substance um, called surfactant to break up those hydrogen bonds. And think of it kind of like a detergent, like dish soap. When you get, if you've ever done baking and you're supposed to grease the pan before you put stuff in, you get butter all over your hands, right? You kind of put it all around, you got butter in your hands, you try to get it off with just water, it doesn't come off, right? So you need to get some dish soap on there, because dish soap gets between the fat molecules and breaks them up, right? That's what surfactant does with water molecules. It gets between those water molecules, breaks those hydrogen bonds, so then the walls of the alveoli can kind of just, they're not sticking to each other, right? And again, that surfactant was made by those type 2 pneumocytes, but those type 2 pneumocytes only really come into full function in the last 2 months of pregnancy. And so premature babies like this little guy here aren't making it yet, right? And so that's one of the big problems, and why preemies have to be on ventilators, is because they need to forcefully open up their alveoli, because they're not really making surfactant yet. They can be given some surfactant, but they need a lot of help breathing because of that. My wife was a NICU nurse for quite a few years, and Yeah, some of the smallest babies she ever saw were like 26, 28 week, full term pregnancies, 40 weeks. So that's only a little over halfway. But like they're like as small, they can fit in your hand. They're so small, one pounders sometimes. And yeah, so just incredibly small. But that's one of the many issues that they'll have developmentally is their lungs because of that. So um, yeah, and this is just kind of a diagram of what that looks like, right? These water molecules on the edges of a alveoli kind of stick to each other and pull those walls with it. And so surfactant is these little yellow things that get between them and break those hydrogen bonds so the walls of the alveoli can stay open. All right, questions about any of that? We can be done early on a Friday. Let's do it. Have a great weekend, guys. Have a good one. All right, see you later.